Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Standard context structure taking P to the origin in R3. So locally, all context structures look the same. Now we want to state a similar result about surfaces inside a contact 3 manifold. If we have a surface Y inside M, then generically the intersection of the tangent plane, the tangent bundle of Y with the contact plane psi give rise to an oriented singular foliation of Y. This is called this characteristic foliation. By singular foliation, I mean it has singularities like the ones I've drawn at the bottom. So the top theorem there just says that the germ of the contact structure near Y is completely determined by the characteristic foliation. In other words, we've got two surfaces, Y1 and Y2, inside 3 manifolds M1 and M2. And if there's some diffeomorphism between the Y's that preserves characteristic foliations, then this diffeomorphism can be extended to a contact isomorphism from a neighborhood of Y1 to a neighborhood of Y2.
So this characterization of contact structure, how it looks in the surface, doesn't assume that the surface is generic in
Well, in order, I think you can find, the way I stated it, you might have to perturb the surface slightly to get that foliation to be, actually a foliation with regular singularities. So, yeah, so I think I did say, that you get this, it's generically. Okay, and then there's a big dichotomy in the, so this is a very selective view of the subject of contact structures. I'm not going to talk about boundaries of symplectic 4 manifolds or anything. And we're more concerned with classifying contact structures on 3 manifolds. And the first step is, well, first we need a definition. An over-twisted disk in a 3 manifold is a disk that is not properly embedded, just somewhere in the 3 manifold, such that the boundary, along the boundary of the disk, the contact planes correspond with the tangent planes of the disk. And so if you look at the characteristic foliation, it might look like the picture there with sort of a limit cycle on the boundary. Properly embedded would mean like the boundary of the disk intersects the boundary of the 3 manifold. I'm saying it's not that way. Okay, well, if you shave off the boundary, then they're the same. And so we say that M, the contact 3 manifold M, is over-twisted if it contains an over-twisted disk somewhere. And then if it's not over-twisted, it's tight. Now this is an interesting dichotomy because I guess Eliashford proved that the natural map, so you take the set of over-twisted contact structures on M, and then you can just look at the homotopy class of the plane field, just some discrete, usually infinite set. It's always infinite. And that's a homotopy equivalence. In other words, any two over-twisted contact structures whose plane fields are homotopic are actually can be connected via contact structures. So classifying over-twisted contact structures, this comes down to standard algebraic topology, and what's left, the more interesting and difficult cases, are the tight contact structures. Okay, so now we're going to stop contact structures for a while and talk about TQFTs. And the next few sheets are taken from some other talk, and so I'm going to go through them pretty quickly because I don't want to get bogged down in this. But we can think of, we're going to think of a TQFT as some kind of functor from manifolds with all this structure, which I'll review in a moment, to something else that mirrors that structure. So if we're used to dealing with manifolds as object that we would cut and paste, we have a category m sub I. These are manifolds of dimension I. We're interested in them up to some top dimension d plus 1. There's a boundary map from I manifolds to I minus 1 manifolds. There's an orientation reversal map, which is an involution on that category. We can take the disjoint union of manifolds. We can glue manifolds up along closed submanifolds of the boundary. It's called gluing without corners. And we can also glue them up along, not submanifolds of the boundary that aren't closed. This is gluing with corners. There's a map from I manifolds to I plus 1 manifolds, which is taking a product with an interval. And finally, boundaries, or more generally embedded codimension 1 surfaces in manifolds have collar neighborhoods. Okay. So for our purposes, that's what manifolds are. This works best with piecewise linear manifolds, but with work, you can talk about smooth manifolds, which is what we're going to have to do when we apply it to contact structures, and then we're going to have to worry about the angles of the corners and things like that. It gets a little messy. Okay, so fields is some functor from manifolds that preserves all that structure. And I mean functor in the loose sense. So first, the examples of fields is given some manifold X, we could take the set of all maps from X to some other space B. Or given X, we could think of all the pictures we draw on X, for example, all the codimension 1 submanifolds, all the trivalent graphs we can embed, that kind of thing, some kind of diagram. And so we were sort of abstracting the properties of those two primary examples. So, by a field, it means we get a functor from manifolds to sets, or maybe some other category. They're restriction maps. We restrict the field to the boundary. There's a bijection between fields on M and fields with M, negative M, the orientation reverse. If we take the disjoint union of two manifolds in the fields, it should just be a simple product relation. And then this gluing, basically this is a fiber product relation. It means if we take a manifold and we cut it and we want to understand fields on the glued manifold in terms of fields on the cut manifold, it's just saying that we just look at fields on the cut manifolds which agree along the gluing surface, and this is in category theoretic language, it's called the equalizer of these maps. All those properties are generally easy to verify, and then something that's going to be a little harder for when we try to fit contact structures into this framework is this taking a product with I. Because the fields, if we've got a field on M, there should be some product field on M cross I. And it's pretty obvious how that works with maps or with pictures drawn inside M. Okay, then a short thing here. Often we define a vector space Z twiddle of M with some boundary condition C is the set of all functions from fields on M with those boundary conditions in to say the complex numbers. So this is just it's a kind of dualizing the fields or linearizing them. Now, given that initial setup, we now look for local relations on the fields, and that's where the sort of meat of the subject is. So, again, this definition is maybe more complicated than it needs to be, but basically we want some kind of equivalence relation of fields that's definable within a disk. That's what local means in the topological sense. So if the locality is the main thing, then these conditions 1 or 2 are relatively minor by comparison. We want this equivalence relation to be at least as strong as isotopy. So if we have two fields and they're related by some isotopy of the manifold, then those should be equivalent. And finally, subdisk consistency means that if we were to take our initial disk and divide it into bunches of smaller ones, and then look at the induce equivalence relation there, then we get the same thing. So that, if we want to check whether two fields are equivalent, we can take a cover that's as fine as we want to, and then just look at equivalence within those small disks. So given a local equivalence relation, we can now define a vector space Z of Y. This is for a d-dimensional manifold Y, so one less than the top dimension. Which is,
Can you say a little more about subject consistency? I mean, if you put the isotopy, you wouldn't see the matter how big or small the disks are.
it's more just the statement that you can refine the cover and it doesn't affect.
So we think that in each disk you have some local equivalence relation defined. And
Right.
if you had a finer cover, there'd be more relations present in each disk.
Actually, there'd be fewer because, well, like for example, suppose our equivalence relation is just isotopy and nothing more. So in this case, the subdisk consistency means that the isotopy equivalence relation on, say, a large disk is generated by the isotopy equivalence relation on some perhaps fine covering of a large disk. In other words, we can take a refined cover and then look at the equivalence relation generated by just doing things within each of those disks, one at a time. And that should give us the same answer as if we just took a big disk. In any case, this axiomatization is, it may be more trouble than it's worth. I mean, there's concrete examples, and one can verify that everything works for the examples, so it's not clear how much mileage you get about formalizing what those examples have in common. Okay, so the basic construction is this vector space Z of Y with some boundary condition C, which is the set of all crude functions in Z tilde. Well, it basically means the function is invariant under the equivalence relation. That's maybe the right way to say it. And then dually, if we just take fields, the C tilde with a bar, it's linearized fields, we can take linear combinations of fields on Y, and then we divide out by the relations there. And we get some vector space, which is often, say, finite dimensional in interesting cases. And that's our main object of study. Yeah, I guess I probably got time. So some standard examples that fit into this framework. If our fields are pictures on Y, there's some subcases. We could take the Timperley-Leib example. So our pictures are unoriented one manifolds containing, say, a two manifold Y. And then our local relations are isotopy. That's always got to be in there. If we see a trivial loop, we can replace that with some factor or lambda. Lambda is a parameter of the theory. And optionally, we can set this piece of n as some particular linear combination of diagrams inside that box. And we set that equal to 0. And then that gets us to a finite dimensional theory. And these are related to the usual Turayev-Vero variance. Another example, if you're familiar with Greg Kuperberg's spider paper, then everything in there is, a similar example with more complicated pictures, trivalent graphs with labels and oriented edges. More general stills, we could just have some diagrammatic algebra modulo these relations. Again, it's not mean much unless you're already familiar with that examples. And finally, from the von Neumann algebra subfactor world, these planar algebras that Jones defines fit in as well. If we take our fields to be maps into some space B, and say we take B to be the B gamma, the classifying space of a finite group, then this gives rise to the Dijkgraaf-Witten theory, so Chern-Simons with finite gauge group theories. The local relations would be homotopy of the maps. You have to check the homotopy in the range is at least as strong as top A in the domain. And then we can possibly twist by some d plus 1 co-cycle on B. Okay, so all those examples are all sort of well understood, and the point of this talk is trying to expand. So we've got this big machine, and we want to find something new to feed into it, and then turn the crank and see what comes out. Another important part of the subject is gluing formulas, gluing theorems. And I guess I want to emphasize that you can prove these gluing theorems once and for all just using this sort of very general properties of fields. So it's kind of a word-saving device. And let's see, how much do I want to? Okay, so given this manifold Y, and it has two matching parts of the boundary, say plus R, minus R. Everything's oriented, so we need opposite orientations there. And we want to know, we want to express the vector space for Y in terms of for the glued manifold in terms of the cut manifold. And to do that, first we have to notice. Well, first we'll make a definition. This is a one category A of R, and the objects of this category are fields on R. And the morphisms are linearized fields going from A to B. So it's just kind of a special case of this vector. We just look at our basic vector space construction, and we do it on a cylinder R cross I. And we can glue those together if the boundary conditions map correctly, and we get a category. And then we notice that the vector spaces for Y, and this is a family of vector spaces because we can put various boundary conditions of plus or minus R, and this affords some representation of these categories. And in fact, if we define Z of R to be the representation category of this thing, then Z of Y, thought of as a collection of vector spaces, is a representation of this category. So get a relation like that. So back to the case of interest, we actually have the product, A opposite cross A. A opposite just means that multiplication works in the other direction. That's because on one side of that gluing area will be stacking to the right and the other to the left. And so the most general statement of the gluing theorem is that the vector space for the glued manifold Y sub GL is a universal object such that one, for all boundary conditions on R, there's a map. The maps are going the other way because Z is functions. And then we've got this commuting diagram for all morphisms. And what that boils down to topologically is if we have some, let's see if I can point. If we had some, imagine some collar around R right there, and we had some diagram in it, we can push it across. And if you take this annulus on one side of the gluing locus versus the other, it's not, once you glue up, they're going to be isotopic. And so this is just an algebraic statement of that fact. And the meat of the theorem is that's the only equivalence relation you have to worry about. There's nothing more. And then there's a dual gluing theorem. Then finally, we're not going to use it today, but the codimension 1 gluing theorem seems too trivial to me. So there's a codimension 2 version. And so, the hope would be that we could get some mileage out of this. Anyway, so this would be slicing up our D-1 manifolds into cutting along D-2 manifolds. In this case, we have a 2 category that acts. I guess I won't go through the details of this, but just try to give you a flavor of it. This 2 category is constructed out of the 0 morphisms are fields on P, the 1 morphisms are fields on P cross I, and the 2 morphisms are linearized fields on P cross a disk. And you can glue these this together vertically and horizontally, and so it satisfies the usual two-category axioms, and then you can define an action of a two-category on a collection of categories. And then now if we're gluing up this, we have a manifold R, and we want to define the category R in terms of this collection of categories we get by cutting it. There's a similar looking set of axioms, and you can say it's the universal category such that, well, so that a bunch of commuting diagrams are defined. I guess I shouldn't, I won't spend too much time on this because we're not going to use it today. Okay, so that's it for our quick review of TQFTs. So now back to contact structures. And our key observation is that the condition of being a tight contact structure is a local condition in the appropriate sense, meaning certainly whether something, the contact condition is local in the, in the differentials, it's just an infinitesimal condition on the plane field. But an over twisted disk is an embedded disk, so it's embedded in a 3-ball, and therefore it's local. So if you're familiar with the contact subject, that's a little counterintuitive because one's accustomed to thinking of over twisted disks as potentially being quite large, and that's why it's difficult to tell whether they're there or not. You might have to look, off in the far corners of your manifold. But still, in the topological sense, they're contained in a contractible region, and therefore it's a local condition. So we can try to apply the gluing theorems to the problem of classifying tight contact structures. And I should make the disclaimer now that this is kind of work in progress, so I'm not going to classify tight contact structures by the end of this talk, but we'll try to make some initial progress in that direction. And we'll in some sense reduce it down to just some combinatorial questions. So you sort of wash all the topology out of the subject, and it just comes sort of a combinatorial question about pictures you can draw inside a two-dimensional disk. Okay, so I said contact structures fit into that framework, but actually if you were to go through and try to check all those axioms, there'd be some technicalities. One is that we're dealing with smooth manifolds, and so we have to be careful about gluing corners. I'm not going to say too much about that, but the other is you need to be able, what's the restriction of a contact structure to a two-manifold along a boundary? Well, we saw before that all the information about a contact structure near a boundary was contained in the characteristic foliation. So we say, okay, to a three-manifold, the fields are contact structures, and to a two-manifold, the fields are characteristic foliations. But then we have to verify that we can take a product. That it turns out in the proof of the gluing theorems, one needs that property, and it's not true that any characteristic foliation has some product field, but it is true generically. So that's the next topic here. So we define a convex structure on. Yeah.
So you're saying the smooth category is a little bit problematic. Is there a FPL analog of the convex structure or FPL version?
Yeah. That's a good question. I've thought about that, and not that I know of. So not that I've been able to think of, and not that I've seen in the literature. So maybe someone has one, but it's not well publicized. But yeah, it'd be nice if there were. Okay, so a convex structure on a surface Y contained inside a contact three-manifold M is a product neighborhood of Y, Y cross I, such that if we take the contact structure from M and we restrict it to that product neighborhood, it's invariant in the I direction. And then we say Y is convex if it has some convex structure. Typically, a surface can have more than one convex structure. And then finally, if Y has a boundary, if it's like some properly embedded surface, then we require that sort of a technically convenient condition is that the boundary be Legendrian with non-positive twisting. Okay, what does Legendrian mean? Legendrian means that that just the boundary of y as a one manifold is tangent to the contact plane. So as we go along the boundary of y, the planes always contain that boundary. And then along that circle, we have two sets of planes. We have the contact planes, and then we have the tangent space of the surface. And so there's a relative twisting, and that should be non-positive. Okay, so the first question is, well, do convex structures exist at all? It's not obvious one can find such a thing. But one theorem in the subject is that if the characteristic foliation is generic in the Morse-Smale sense, then Y is convex. Okay, so what does Morse-Smale means? That there's no connections between saddles, that there's a finite number of singularities or limit cycles in the foliation, and that along each one-dimensional limit cycle, it's either sort of linearly attracting or linearly repelling. You won't have a limit cycle that kind of repels on one side and attracts on the other.
Can that get you for rotation of Y?
Yeah, so the next theorem is any Y is C infinity close to a convex surface. Okay, so that kind of solves our, this is just one of the technical issues we have to resolve in applying these sort of piecewise these techniques of TQFTs that are best suited to piecewise linear structures and try to get them to work in a smooth context. Okay, so now.
I mean, there's some kind of irony that people invented TQFTs didn't even know what a PL manifold was, right?
Yeah. Yeah. Well, yeah, I think that is, TQFT means different things to different people. So, okay. So so our goal is to take a three-manifold, cut it up into small, simple pieces, understand contact structures on those small pieces, like maybe there'll just be a three-ball, and then reassemble to get information about the tight contact structures on the big three-manifold. And when we do the reassembly, we're going to be using the gluing theorems. And to apply the gluing theorems, we have to understand those categories that were defined along a boundary. So let's take a look at the category A of Y for some surface Y. This is a category whose objects are Morse-Smale foliations on Y, as defined above, and then morphisms are contact structures on Y cross I. And then composition of morphisms, we just stack them together. So you agree. The first thing we want to do is try to simplify this, because there's obviously quite a few Morse-Smale foliations, even if we consider them only up to isotopy. That's a lot of possibilities. And so we want to ask, what are the isomorphism classes of objects in A of Y? And it turns out that there's a surprising simplification. But I'm just defining what an isomorphism class of object means. If you've got objects A and B in a category and maps F and G, so that if you compose them in one direction, you get the identity on A. Compose them in the other direction, you get the identity on B. So, preparation, let's make another definition. Y cross I is the convex structure, so it's got this I invariant contact structure. The dividing curves of Y cross I is the one submanifold for which the contact planes are vertical in the I direction. That doesn't, we need some specific convex structure for that to make sense. You can, the perpendicular to Y doesn't have any meaning in just if Y is just a surface sitting inside a contact three-manifold. You actually need this product structure before you can define it. Though it is true that if you were to pick a different convex structure, the dividing curves would change only by an isotopy. And so it's not hard to verify that the dividing curves are transverse to the characteristic foliation and divided into a maximum number of sink and source regions. So we've got, and there's an oriented foliation. It's got sort of expanding singularities, contracting singularities, and then in the expanding region, the sort of orientation of the contact planes and the surface agree. In the contracting region, they're the other way, and then the dividing curves are sort of the interface between sort of positive and negative relationship between the tangent space of the surface and the contact planes.
Are there also shallow singularities?
Yes, there are, but they They're kind of neither expanding nor contracting.
So where do they lie with respect to the dividing curves?
Yeah, they would like, I mean, since the dividing curves are transverse to the foliation, it won't pass through any of the point singularities. Okay, and so the main theorem about dividing curves for our purposes are if A and B are two characteristic foliations on Y, then A is equivalent to B in the category theoretic sense if, it's not if and only if, but just if A and B have isotopic dividing curves. In other words, if you've got this product context structure on Y cross I, let's say it's with respect to A, if the dividing curves of B are the same, then we can find some perturbation of Y inside Y cross I. I should have drawn these blue curves to be the same. We can kind of tilt it, keeping it perpendicular to the I direction so that we can change the characteristic foliation here to basically anything we want to that's compatible with the dividing curves. And then, of course, these morphisms, this F and G work in the same as the previous definition. So this is good news. It means if we want to consider we want to understand this category for a surface, instead of having to consider all possible Morse-Smale foliations, we just have to consider all possible dividing curves. In other words, all ways of dividing the surface into positive and negative regions. And we can simplify things a little bit more because we're actually interested in tight contact structure, and it's possible that for a given set of dividing curves, there might be an over-twisted disk just contained in the neighborhood of the surface. And so the next theorem says that Y is tight if and only if there's no trivial loops in the dividing curves, or if it's S2, it has only one trivial loop. So the shorthand way of saying that is there aren't any more trivial loops than necessary. So just restating it down here, up to equivalence, the objects in our categories are isotopy classes of one manifolds without trivial loops, or at least without more than necessary. And then there's also a shape, the regions are labeled plus and minus.
What is A of Y again?
A of Y is this category whose objects are of infinitesimal contact structures, and the morphisms are contact structures on a cylinder. And so our big job is to understand A of Y and its representations. Okay. So before going further, we need to cover some technicalities about corners. Because if we're slicing up a smooth manifold, the pieces are not going to have a smooth boundary. There's going to be corners, and we need to understand how these dividing curves change around a corner. Now, along each corner, I haven't restated it here, but we have the Legendrian condition, so we can assume that the contact planes are spinning in some kind of negative direction along the corner, and we know that if the plane, and so we have convex structures, I invariant contact structures in the neighborhood of these two sheets, but if the plane is perpendicular to one, it can't be simultaneously perpendicular to both of them. So that means the dividing curves are not going to match up. And if we had, say, a 90-degree angle, they're going to alternate. You see these sort of horizontal dividing curves coming in along the top surface, and then vertical ones coming on the bottom, and they alternate. And then if we were to smooth the corner, they would hook up. And basically the rule is you move to the right. If you've got, because it's also tangent to the corner. The plane contains that corner of one manifold. Yeah, that's the Legendrian condition, which is.
Which line of the picture one's getting back? Does the corner come into?
Yeah, it contains. Right. And again, if we were just smoother things out, they would connect up by this move to the right convention. Another interesting case is we might want to make the angle, it's a very sharp corner, make the angle 0. And so then the dividing curves do match up because the surfaces are tangent as they approach, but the plus and minus regions are opposite. If you've got something that's oriented positively with this surface and it's oriented negatively with the one on the bottom. And so to hook them up, instead of the obvious way, just like this, you have to actually move one click to the right. And that, if you were to smooth out that sharp corner, that's how the curves will go together. And so this is just giving an illustration of it. We take a torus with these boundary curves, we cut it along a disk, and then I guess this picture got a little too small, but you can see that the dividing curves on our original boundary, don't match up to the dividing curves on this disk, but they're kind of connected together in that fashion. Okay, so now we're ready to start computing. And what's the simplest surface we can think of? It's the disk. And we have to give the disk some boundary condition, which is the sort of twisting number of that Legendrian curve along its boundary. And if that Legendrian curve has n twists, that means that the dividing curves are going to have 2 n endpoints on the disk. And so the object, so we have a family of categories parameterized by n. If n is equal to 1, there's only one object. If n is equal to 2, there's 2 different ways to connect up 4 points. If n equals 3, there's 5 different ways, etc. And one nice thing is that these curves in a disk are, these are old friends in this subject. One studies them all the time, so it's kind of nice to have them popping up surprisingly in this situation. Okay, so we understand what the objects are in these categories. Next, we want to understand what the morphisms are. So the morphisms are tight contact structures on D2 cross I. Because we've got the boundary, we need to make some convention about the boundary. And the one I like is you actually pinch the I direction to 0 along the boundary. So think of some kind of lens-shaped, 3-dimensional object. And so we have angles 0 along the boundary. And the nice thing about these is if you glue a bunch of them together, then you get another such thing, the angle. So 0 plus 0 equals 0. Okay, so if we want to know the morphisms between 2 objects, we put one picture on the top, we put one picture on the bottom. Along the edges, we join up the curves like we did on the previous page. And then we ask, okay, how many tight contact structures are there on the 3-ball with those boundary conditions? And there's a theorem, an old theorem of Élie-Ochberg, which gives the answer. If a contact structure is tight on a neighborhood of the boundary of B3, then it has unique kite extension to all of B3. So that means that there's going to be either 0 morphisms or 1 morphism between any 2 objects. That's really simple. So here's sample calculation for the n equals 3 case. In the top row, we look at the morphisms and going for some object to itself. We hope that we find one because there ought to be an identity morphism or something to itself. And so it's on the right-hand side, I've drawn, this is sort of a picture in S2 where I've taken one of the hemispheres and I've folded it out to infinity. So you draw one diagram in the interior, and then you sort of invert the other one to the exterior, and then you join up. And we see that when we connect all the curves up, there's only one loop. And so one loop means, by one of our previous theorems, that the boundary is tight, and therefore there's a unique tight extension. So we do have a morphism from something to itself, i.e. the identity morphism. Now, if we look at the morphism to something that rotates one click, we see that we again get one loop, and so there's some morphism going from there to there. And this is actually going to play an important role in the subject. This is the sort of standard elementary morphism from a disk to the disk, with these sort of n equals 3 boundary conditions. We'll see later that for a general surface, every morphism can be decomposed into things that look like that, and they're the identity outside it. And then finally, if we look at clicking once the other direction, we join up, we see that we get 3 different loops here. So that means that that's over twisted even just in the boundary. So there are no tight, there are no morphisms between those 2 objects.
Is there a direct connection between loops, separating curves and boundaries?
No, the way you prove that theorem about too many is what you do is you notice that if you've got an extra, a trivial loop, then remember we're free to sort of put any, the dividing curve just gives sort of an equivalence class of infinitesimal contact structures in the neighborhood of the surface. And then the sort of one of the big theorems on the subject is that we can so we can pick a characteristic foliation compatible with that, and so you sort of construct a characteristic foliation that obviously has an over-twisted disk, a disk with a limit cycle.
How come on the case that he's free to get away with one circle without that?
Yeah, it's because let's see. Okay, so so say here's a dividing curve, and then there's more surface beyond it, so there's a trivial one. So we start out, the characteristic foliation, which I'm drawing green, is transverse, so we can put a singularity in there, and then we can just make a limit to a cycle. Okay, so here's our over-twisted, okay, so there's an over-twisted disk, and the question is, can we complete this to the rest of the surface? And it turns out if the surface has higher genus, you can do it no matter what the dividing curves are like. But if it's the 2-sphere, and suppose we were to try to complete this to the 2-sphere and we didn't have any other dividing curves, we had only this one, then you'd see that this isn't actually dividing curve. So here's some attracting limit cycle, and there could be another one coming from the outside and another singularity out here, but what it means is that, well, there's actually got to be another dividing curve if we were to do that. And so there's sort of no way of patching up the foliation on the 2-sphere with this restriction that there are no other dividing curves. But on a high genus surface, you can, regardless of what the other dividing curves look like. Okay, so to describe a category, we've got to do 3 things: objects, morphisms, and a composition rule, and we've done 2 out of 3 so far. So we can now draw the objects and the morphisms of these categories. N equals 1, we just have 1 object, and we've only got 1 morphism, trivial morphism. N equals 2, we have 2 objects, but again, only trivial morphisms. Things start to get more interesting at N equals 3. We have 5 objects total. These 2 are isolated. They don't connect the morphisms to anything else, but these 3 are connected in a triangle. That's the calculation we just did up there. And then we also have identity morphisms in addition to ones that kind of rotated around. What we don't know yet is if we take this morphism composed with that, so that's some morphism from here to here, and is it the 0 morphism or is it this non-zero thing? And then the dots on the arrows mean that they're elementary, and I'll say more about that later. But let me just show a few more examples. Mike told me people like pictures. Here's N equals 4. Oh, and so I've got it takes a long time to draw these pictures, so there's a convention that you can shrink the positive region down to a 1 complex. So instead of drawing a picture like we do on the left on the top row, we draw it as the right. So to translate back to the usual dividing curves, you sort of thicken up the arcs and take their boundary. Okay, so with that convention, we have here N equals 4. There are 14 objects. The top, I'm not drawing the identity morphisms anymore. The top 2 are isolated and don't connect anything. And then the other 2 have that relation. And here's a piece of the N equals 5 category from my notes. I didn't have time to redraw it. Just to show that you can get pretty far just by hand doing this. Okay, but we know at this point for the disks, we can list all the objects, and we've got a very simple algorithm to tell us how many morphisms there are between any two objects. It's either 0 or 1. What we don't yet know is how to compose those morphisms. So that's what we do next. I want to define an elementary morphism, which I've drawn in two different ways with the two different drawing conventions. And it's just that it's something that within a small subdisk, that's with the dotted blue boundary, it's just like that very first non-trivial example we did. And then it's the identity everywhere outside that small disk. Or if we draw it in terms of arcs, it's this kind of move. And notice that this is chiral in some sense. There's a based on our choice of sign conventions about the contact structure, we can rotate in one direction but not the other. Okay, so it's not too hard to show that any morphism is the product of elementary morphisms. And then a more difficult theorem of Eli-Oshberg says that if we've got a series of objects, so each of these A's is some diagram on a disk, and each of these E's is an elementary morphism. So, if we have a composition of elementary morphisms, and we want to know whether the answer is 0 or not. We want to know whether there's an over-twisted disk somewhere in this 3-ball. And what we know is that each of is tight on each of these small slices, and furthermore, each of these slices is elementary. It's about as simple as can be. And so Eli-Oshberg is a relatively simple criterion, which is we just have to check the following family of two spheres. We go from A0, the bottom one, up to some intermediate A, and we look at only at the 2-sphere. And detecting an over-twisted disk in a 2-sphere is easy because it's just a matter of counting loops over previous theorems. So this is, pretty, this can be implemented on a computer. It can be done by hand in small examples. So now we know. So in general, if we've got two morphisms and we want to know whether their composition is 0 or non-zero, we take each of them, decompose them into elementary things, and then put those two things together, and then apply this test.
I think I understand. So I see that you're using type in two different meanings, a 3D meaning and a 2D meaning. Is that right?
Yeah, but the 2D means actually in a three-dimensional neighborhood of the two-dimensional stuff. And then the nice thing about and the thing is that if we're only considered about tightness in a small neighborhood of a surface, then we can check it just by looking at the dividing curves. So it's easy to, this question of whether something's tight or not, we know how to answer it on sort of thin 3 manifolds. And this shows us how to, at least for the 3-ball at least, sort of bootstrap our way up to answering questions about tightness in the larger manifolds. Okay, so at this point, we've at least, we've given an algorithm for answering any question you could ask about the category. So let's apply the gluing theorem and try to compute some bigger 3 manifolds. For example, you can take a 3-ball and glue it to itself along 2 disks and get a solid torus. So we should be ready to compute contact structures on a solid torus with given boundary conditions. So TCS means tight contact structures on S1 plus D2. So we fix in, we consider S1 cross D2 with n comma n boundary conditions, and that actually means 2n longitudes and 2m meridians. So I've drawn the case n equals 2, m equals 1 there. So it's ignore the bottom. So what does the gluing theorem tell us about in this situation? I probably should have drawn some more pictures here, but so in some sense, we're taking the disk and we're gluing it to itself with an m over n twist. So let T be that map. M over N twist, and the D2 with some boundary conditions of self. Then the gluing theorem tells us that the tight contact structures on this thing are in one-to-one correspondence with the following set. So we've got a set modulo equivalence relation. The set is the set of all morphisms going from A. A is an object in the category, i.e. A is a picture on the cut disk, and it takes us to the T star of A, the twisted version of that. And so that's, of course, what you would expect. You know, you've got the solid torus and the boundary conditions twist. You cut it, and well, that's geometrically obvious. The equivalence relation is that if we've got a composition of two things, if F, say, is equal to G composed with H, then that's equivalent to H composed with twisted version of G. In other words, if we've got this arrow down here going from A to T star A, so that's something in our set, and we can decompose it, you know, via some intermediate morphism B, then this is equivalent to the one up here where we take G, we twist it, bring it over here, we get a new composition. And all that, the geometric content of that is actually pretty simple. Here's a solid torus. You know, we cut it, we get A. But we might choose a different disk and get a B. And so, you know, G would be the thing connecting from here to here, and H, you know, the thing that connects all the way around. And so if we put G and H, GH, and glue it up, that's obviously the same thing on the solid torus as H and then G, except it's not really G because of the twisting boundary conditions. We have to use T star G. Okay, so now, so this question of the solid torus had already been investigated using somewhat different techniques and answered in, not in all cases, but this is actually true just if N and I forgot to write, but N and M have to be relatively prime for this theorem to hold. And so you take N over M and you write it as a continued fraction expansion, and the number of tight contact structures is the product of these numbers. So we can try to reprove that, or failing that, we can implement on a computer and at least check. Yeah, so up to N equals 7 or 8, you know, explicit calculations are in agreement with that. The only cases I can prove currently are when M is equal to, the extreme cases of M is equal to 1 or N minus 1, though it turns out that if we want to go on to gluing two handles and classify three manifolds, those are the most important cases. And this is a sketch of the beginning of the proof for the case M is equal to N minus 1. So what does this mean? So we take some diagram, and now I'm using the thick arc convention. And we assume we have some, well, you can actually show that there's always a non-zero morphism from this to the thing where we've rotated the boundary by one click on this lower picture. So that's like our F in the previous page. And now we want to factor it, and the factoring will give us some equivalence relations. And so the factorization is, first we rotate A and B individually inside their own disks, sub-diagrams. Then we apply one of the elementary moves. We're going to cut right here and then reglue it right there. That's, you know, something taking place in a small disk, so that's an elementary move. And then we do the same thing here. We're going to cut and reglue there and get back to where we started. And so this is an elementary move. This is an elementary move. And these are, you know, there's a bunch of elementary moves. That's in the, if you draw them the normal way, but this is... Well, but let's see, this is an endpoint, so this would only be 1, 2, 3. You know, draw. So it's thickened version of I've got this, and then the boundary would look, the boundary of the neighborhood of the green arcs would look like that. So 3 red arcs.
For the downward right arrow, you have like 2 red strips.
Well, you would draw the picture that it goes only halfway through the thick red strip, or there would be some extra stuff in the picture, one or the other. So what we want to check is that this really is a factor. Okay, so we've got a bunch of morphisms and they go from here to here, but how do we know that when we put them all that this is a non-zero decomposition? But you can check that, and then once you check that, it means that morphisms starting in a picture like this are equivalent to ones starting like this, or like any of these intermediate pictures give the same thing on the solid torus. And armed with that, you show that really the only invariant is the number of components of these thick red arcs. And so let me bring a previous picture back up.
In this picture, why isn't the beginning one and the last one just like the
Because the boundary is fixed. It has to be isotopic on the identity of the boundary. So if we look at the n equals 4 case, we find that the category falls into 4 pieces, and this is given by the number of components of the red graph. This is 4 components, 1 component, 2 components, and 3 components. And what you show is that any 2 things in here for the n-1 twisting case are equivalent, and that's true in general. So that's just a flavor of the calculations you can do. So that's it. At least that's as far as I've got prepared stuff.
What
But
about where this might head?
yeah, so I guess one could try 2 things. One would be a better understanding of tight contact structures on 3 manifolds. So far, it's just managed to reproduce some of the existing results, but yeah, I think there's reasonable hope that it could go further. And then the second thing is sometimes, but not always, TQFT defined this way, you have a D plus 1 dimensional piece. And so that would mean there would be some 4 manifold invariant that's related to tight contact structures on the boundary. And this is very suggestive because the sort of Seiberg-Witten, Ojvat-Szabo invariants have a known sort of map onto tight contact structures. And those things fit into a TQFT, or at least they appear to. And so this one could hope combinatorially to construct the sort of target TQFT of those known maps that just operate on the 3 manifold pieces. There, so that's the longer term goal.
For this finite dimensional vector space that we're putting space is there a representation
Yeah, there would be. Yes, that's how it permeates. Right. I mean, in some ways, it's kind of overkill to call these vector spaces, because if you look at the matrices of the morphism, the entries are always going to be 0 or 1. So we could tell this whole story just with sets instead of vector spaces. But in any case, yeah, the mapping class group acts on tight contact structures.
Because what you just said, it would not be against action, for example, like
Yeah, I don't think it would. Yeah, it doesn't look like it's a good candidate. Also, it's not. Well, let me leave it at that.
what is the manifold of other partial classification results, which is on this scale?
The most popular thing seems to be for closed theory manifolds, Breeze-Korn homology spheres. There are, I'm trying to think. I mean, there are examples of manifolds which have no tight contact structures. That's a recent result. I think it's a connect sum of two with like opposite orientation, so it's not a very enlightening construction. And then I think using some of these relationships to the Ojibwa-Szabo invariants, those give bound. One can prove results, and typically it's about surgeries on knots or Breeze-Korn homology spheres.
So this solid torus example is pretty much isolated. It's a very special case where one can analyze it.
But isolated in what sense?
I mean, this is a particular classification here, but the unknown fits here before.
Oh, right, yeah. So it's not well understood. Yeah, so there's not even. Yeah, I guess there's also no algorithm for computing for a three-manifold, which is another. I think a more likely outcome of this is that you might actually, with work, get some effective algorithm for computing the tight contact structures on a three-manifold, even though the algorithm might not be practical in practice. Already, you can using this techniques, given a handle body and an arbitrary set of dividing curves on the boundary of the handle body, one can compute all the tight contact structures. So that's, I think that is a new result, or at least it didn't.
What's missing to get out of these?
Okay, you'd have to, so pretty much, zero handles and one handles are well understood, and so the next step would be considering gluing in a handle decomposition of three-manifold. You want to understand two handles. And so one, part of the reason we're interested in the solid torus is that that's the building block of the category that we get for where we replace the disk by the annulus. Annulus cross I is a solid torus. And so this is sort of telling us how to compute what all the morphisms are in that category. We don't, with a little more work, we can get composition. So that's the motivation, part of the motivation for doing the solid torus first. Once we do that, then we can try to describe gluing two handles on. The problem there is that there are infinitely many objects. Even for, the nice thing about the disk is once you fix boundary conditions, there's only finitely many objects, and all the categories are finite, and so you can get finite algorithms to check things. On an annulus, you can have sort of, even with empty boundary conditions, you can have arbitrarily many sort of rings running around the core of the annulus. And so it's going to take a little bit more work to turn that into dividing curves.
But if there are too many dividing curves, I thought you said that for the example out,
no, only if there's too many trivial dividing curves.
So what about parallel?
That doesn't matter.
That doesn't matter?
Yeah. But anyway, if one could solve that, and I think it's reasonable to think one might, then you'd be done, because gluing on the three cells is trivial. So.
What do you think about the relation of this TQFT and the one that you get as part of that?
Well, one, back up one slide. So if we look at the category, just the first place where the category gets non-trivial, the n equals 3 case, it turns out that the composition of these two, actually it has to be 0 because there's no morphism going from here to here. I misspoke before when I said I was on the way. There's a morphism going this way, but there's none going reverse. So we know that these two composed with each other are 0. And that's sort of a simple example of the sort of nilpotent property of these categories. And then more generally, let's look at the part of the n equals 5 example. There's a sort of circular symmetry to the category which comes from rotating the disk. And morphisms tend to prefer to go one direction and not the other, roughly. And if you go too far around, you tend to get 0. If you look at the Ojelva-Szabo categories for, say, the torus, they don't have anything for surfaces with boundary. There, the object would be a Hagar diagram on a torus, i.e. it would just be a line of some rational slope, which again has a circular structure, the rationals sitting inside RP1. And it's also the case that morphisms only go one direction around the disk, and if you wrap around more than once, you get 0. So there's this sort of, I mean, that's a pretty crude thing, but there is that similarity. Two torus. You get the categories for two manifolds. Yes. And then also, I guess also the when preliminary calculations doing the contact thing for the two torus, you get this sort of handedness aspect to it. So that's suggestive, and then also there are these well-known maps from the Ojelva-Szabo things that tie contact structures. So anyway, I guess that's.
So there's some connection, but there are some anti-connections too.
Yeah, they're not the same on the nose. Like if you do calculations for lens spaces, for Ojelva-Szabo, an LPQ lens space always has a p-dimensional vector space, and for the contact structures, you have at most p. Hitting its p in that sort of extremal case where I did the proof. And so one might say, well, okay, the contact structures span the sort of interesting part of Ojelva-Szabo, the part that might be realized by a bounded 4 manifold. But that can't be true on the nose either, because there are 3 manifolds which have infinitely many tight contact structures. So this is going to be. Is always in different examples. So it's clear, so it's not. It's kind of too early to even guess what the right answer would be. But on the other hand, I think there is strong evidence that there's some kind of connection. So it's worth looking at.
Okay, is there an analog of this to the Baxter equation?
Not that I know of. And if I had to get, I mean, I guess I'm not motivated to look, which means I guess somehow I suspect it's not there, but you can't, maybe surprisingly there would be. So I think in some ways, it's just, the pictures you draw on this subject are just the same as the ones you draw on the, familiar Chern-Simon stuff 1 dimension down. But I think maybe that's mostly a coincidence and not evidence of some deep relation between the theories, but I could be wrong.
No, I just think the pictures are kind of setting out
Yeah, so I don't want to discourage you from looking, but I'm not currently looking myself.
Nobody asked me if we were looking for it.
Oh.
It's much.
Oh. Oh.
That's all.
Oh.
So you don't still, I remember guessing,
I knew,
talked to you.
but I didn't associate your face with your name.
Oh, okay.
Okay. Why don't you do this?